This class, the intention of this evening's class is to look at this example we looked at last time and really go and explore it in depth. And while we're exploring it, we'll learn a bit more about some of the heat equations we've been looking at over the past few classes. So just to recap for that heat equation, heat balance that we've been looking at, this is probably the most important heat balance derivation we ended up with. There were several steps, but where it ended up with is our heat balance. We have this term Q naught, Q dot. We have the flow of A coming into our system with P naught. So T minus T naught minus the heat of reaction here times delta multiplied by the conversion x. Okay, so this is a heat balance at steady state. And as I said, it's a pretty important equation. There's a few assumptions we made along the way to get there. So let's just take note of some of that here. Q dot is, let's be clear on our sign convention here. This is the heat entering the system from outside. Okay, and then of course if Q dot is equal to 0, then it implies it's an adiabatic. So make sure that if heat is entering your boundary, that it's positive. If heat is leaving, that Q dot needs to be negative. Cp naught is a weighted sum of the heat capacities weighted by I, Cpi. T is the system temperature, T0 is the inlet temperature, and delta HR is the heat of reaction. So when we've got negative delta HR here, it's not implying anything else other than take the heat of reaction and multiply it by a negative sign. So for example, in an exothermic reaction, we have a negative inside the bracket and a negative outside the bracket as well. We're going to look at some of the concepts around this heat balance in this evening's class. Then we looked at this example yesterday, so you have most of this information down already. There is one small mistake I made in the last class is I specified the resonance time as 10,000 seconds over the wrong value. Well, it's actually 6,000 seconds. So please update that in the notes. So it means that we've got about 100 minutes resonance time in this CSTR. So again, let's just draw a picture of what we're dealing with. We're visualizing this correctly here. I've got my CSTR reactor. Around it, there's a jacket which is providing heat transfer to the reactor. So there's a certain area here. So that's called T ambient entry temperature coming in. And we've made this assumption also that T ambient is needed. There's an inlet temperature T naught. But that temperature is only the inlet temperature. The contents of that reactor are well mixed. And leaving the reactor then is a certain temperature T. There's also a conversion X and a concentration. All those properties that are inside the reactor are also the ones leaving the reactor. So this U times A term over there, that's a product of the heat transfer coefficient multiplied by the surface area available for contact on the CSTR. So that's where we were last night. We know that as my system changes, operating point, so this temperature changes in this CSTR. If I move to a steady state for a certain temperature, my rate constant K is also going to change. So I've been given my rate constant K at 350 Kelvin, and also what that activation is. So I can recalculate the rate constant at any other temperature. So the aim of this question was, to recall, was if T naught is equal to 450 Kelvin, what is the outlet temperature and outlet conversion? We started setting up the equations for that last night. Where we got also is to a point where we specified kappa. So kappa is a number that's going to be useful in these heat transfer type problems. It's a dimensionless number that's the product of U times A divided by FA naught times CP naught. Well, we've given UA, we're given FA naught. Last night we derived that CP naught was equal to 210 joules per mole Kelvin. Let's just quickly look at that calculation. Just one over here. So CP naught was equal to theta I CPI. In this case, I've got theta I is the ratio of the inlet flows. So I've got no flow of V coming in, so I can disregard V in that summation. I only have A and inert coming in. So theta I CPI, in this case theta A is equal to 1, and theta I is also equal to 1. So it's simply coincidence that my CP naught is this case CPA plus CPI, but it's not always the case. It's just coincidence that thetas are 1 in this particular instance. So CPA plus 125 plus 85 gives me 210 joules per mole Kelvin. Joules per mole, what per mole of my basis species reaction? So joules per mole of A. So when we calculate kappa, then yesterday we had that that's equal to the product of U times A, which we were told 560 joules per second per Kelvin, divided by FA naught 1.3 moles per second, multiplied by CP naught, which is 210 joules per mole Kelvin. So units cancel there, joules cancel, moles cancel, and I get a dimensionless number of 2.05. Also, we calculated TC, and TC has an interesting interpretation. Provides us a bound for our initial guess later on. So let's just take a look at that quickly. TC is equal to kappa times T ambient plus T naught divided by 1 plus kappa. And so if we sub in our numbers over there, we got 341 Kelvin for TC. So this energy balance or heat balance up here, I can actually write it in terms of kappa and in terms of this new variable TC. So we can rewrite this, shown in the previous class, as CP naught 1 plus kappa T minus TC. And that's going to equal the negative of the heat of reaction multiplied by conversion x. Okay, so you can prove to yourself that you can get to this point from this point up here. If you sub in that definition of kappa and you can sub in that definition of TC, this simplifies back to that starting point over there. No. not equal to 0 because we have heat transfer in the situation. We have ambient material coming in at 300 Kelvin over here. So T ambient in this example is 300. And T naught coming in is 450. So our question that we're looking to answer is, what is this exit temperature T over here? So last night we established that that temperature leaving for sure is going to exceed at least T ambient. We know that for a fact, that T leaving must exceed T ambient, the heat transfer temperature coming in. But we also established last night that we can actually get a slightly better estimate for T from this equation over here. Cp naught is a positive quantity, kappa is a positive quantity. So this all here is positive. Heat of reaction, delta HR, is a negative quantity, but a negative times a negative gets me a positive over here. Conversion must always be positive. So for that equation to hold, T must be greater than Tc. So that's a better estimate of T. So we know that T must at least be the same as or equal to Tc. We also know, of course, that T must be greater than T ambient for any heat transfer to take place. But T ambient was 300 Kelvin, Tc is 349. So we can already eliminate quite a substantial region from our guess. Is there an upper bound for temperature? So we said last night that we're going to apply a guess and check here. Is there an upper bound for temperature that we should not go above?
I think the established was 400.
We established it was 400.
Yeah.
Okay. So there isn't really an upper bound. Like, just by looking at what we've got here on the board right now, we don't have an upper bound. We know that there's an exothermic reaction taking place. If I have a material entering at 450 Kelvin and with an exothermic reaction occurring, if this heating medium is not removing heat fast enough, it's quite likely that the temperature leaving can exceed 450. But we did derive an additional equation yesterday that helped us get an upper bound, and that came from the design equation. So the design equation for this system is the regular CSTR design equation. And the reason why we introduced this is because we recognize that this heat balance equation here has two unknowns, temperature and conversion, that I'm interested in. So we've got one equation with two unknowns. We said last night, an additional equation. Well, our design equation gives that to us. Our design equation is the volume of the reactor, K naught times X over minus RA. And we made some substitutions in there last night that allowed us to get to a point where we said how the residence time of the reactor is equal to the conversion X over K, the rate constant, which is a function of temperature, 1 minus X. So there's actually our second equation. And it's also a function of conversion X, and implicitly a function of temperature through this rate constant K. So two equations with two unknowns. Our two unknowns being temperature and conversion, exactly what we're aiming to solve for over here. And what we can find, what we found last night, we did one iteration where we estimated our temperature to be 400 Kelvin. This K is a function of T. So maybe if I write it as square brackets here. Okay, so good question. That K, round brackets T, implies K is a function of T multiplied by 1 minus X. So my denominator is the product of two terms. So our strategy that we're going to follow is this. If we're planning this, is to guess a temperature Then we're going to calculate K of T. We're going to then calculate our conversion X using the heat balance. And then we're going to substitute into this equation over here from my mass balance. So this is my mass balance. And I'm going to check if it meets or matches the tau value that I know my system is operating. So check means tau. So we did one iteration of that yesterday, where we ended off the class. And there was some questions afterwards that maybe want to go through this again. So I'll just step through our initial guess at 400 Kelvin. Said, well, let me estimate my conversion. My conversion X is given by Cp0 1 plus kappa. So I just take that heat balance equation, rearrange for conversion. T minus Tc divided through by the negative heat of reaction. So if we substitute in those values that we know, Cp was 210. I'll need you to check that the units do actually match. T, our estimated T is 400, minus Tc, which was 349, divided then by 31400 for the heat of reaction. This is my initial guess for temperature. If I do that, I will calculate a conversion of 1.04, which is nonsensical. In fact, any temperature higher than 400 will give you conversions greater than 1. So there is an upper bound on temperature over here. So we know that somewhere between 349 Kelvin on the lower bound and at most somewhere around 400 is where our outlet temperature was. So then we go through our usual guess and check iterations. Actually, one thing that's you should confirm for yourself obviously is if I substitute in temperature at 349, so T is equal to 349, I'm going to get T minus Tc, 349 minus 349, I'm going to get a zero conversion. So any value of temperature below 349 will give you a negative conversion, again indicating that that's a poor initial guess. So we know for sure we're somewhere between 349 and 400 Kelvin. So the next iteration then you can do it in several ways. And what people came to me after the class is, well, how do I know which direction and by how much to step? Well, that's the problem with guess and check. Guess and check is, by definition, an inefficient way of solving problems because we're simply guessing around. But one thing that you quickly get a sense for is by doing one or two iterations is get an idea of the sensitivity of the system. So at 380 Kelvin was my next guess here. We said let's calculate that conversion again, so I won't sub in all the numbers, but using that same equation over there, the conversion you can calculate for yourself is 0.63. I can also then calculate the rate constant Kt. That's equal to 1.1 times 10 to the minus 4 multiplied by the exponent of E over R 1 over 350 minus 1 over 380. So this E term was given to me as 16700. So that calculates at 1.73 times 10 to the minus 4 units or seconds to the minus 1. So then if I sub into that mass balance over there, I'll get tau. Let's call this tau estimated. we know that our tau should be 600 seconds. But let's see if with this guess what we estimate tau to be is 0.63 divided by 1 minus 0.63 multiplied by 1.73 times 10 to the minus 4 from that rate constant. So that gets me estimated tau of 9,842 seconds. Okay, so height, this temperature of 380 Kelvin, I've estimated a residence time that's longer than my actual residence time. Should I go up or down? What do we expect for a CSTR? Longer residence times get do what to the conversion? Okay, so longer residence times get longer conversions. So we've got long residence time. If we want to decrease this residence time to 6,000, that means we want our conversion to be lower. What do we need to do here to our conversion to get this number lower? Bring T closer to TC. So bring my T smaller, make that difference smaller, so bring it towards TC. So let's drop temperature from 380 down to some other number. So my next iteration I might choose, well, I'm bounded between 349 and 380. My next iteration I might choose 360 or 370 or somewhere along there. But let's just take a look here at what, if I'm guessing 360 Kelvin, you can show that the conversion now drops quite a bit to 0.224. Your K value comes out to 1.29 times 10 to the minus 4. And your estimated tau is now quite a bit lower, 2,242 seconds. So over this 20 Kelvin range, we've caused this residence time to drop quite substantially. And that to me is the biggest indicator that I'm not going to get to this answer quickly. Like there's going to be, there's tremendous sensitivity here. With relatively minor changes in my guesses, I'm seeing large changes in tau. So in an exam or so, like you would probably just do one or two more iterations at the very most. In this case, my next one was at 375. I went back up closer to 380. 375 gave me a tau of 7,000. But then the final one that gives you a good enough value is T at 373 Kelvin. So there you find the conversion to be 0.49. The K value at that temperature is 1.567. Just takes minus 4 seconds, and my tau estimated is equal to 6,120 seconds. And that's good enough, given how much this is changing for very small amounts of time.
On the test, if you're for 3 and you're going down by 10 first, then that would make you have to have 3 calculations and step up to 6.
Yeah, you got 380 and 370, and then you're going to see you're too low and you would go back up again.
But what happens with that, you work with 3 iterations, but you're not really too close.
The aim is not to do 3, the aim is to get close. Yeah.
I'm saying like on the test, how would that be marked over? Based on how close you are.
But
Okay.
I would see. I don't know how it is. So here the main aim is that you get reasonably close and that you show that I can see in your next iterations that you're not just randomly guessing temperatures, but you're actually thinking about why you're choosing the next temperature when you're choosing it. Right, so we don't want to waste time in an exam. We want to get it right the first time or the second time or as soon as we can. So think about where your next iteration is and apply it in a sensible manner. Okay, so we've essentially solved the problem at this point. We've got where we wanted to. We've found our conversion, and we've found that rate constant at this temperature. So 373 seems to be the temperature with the conversion corresponding to 0.49. that's okay, that answers it, but I really wanted to also then go to the next step and introduce a little bit more about that heat balance. And let's actually understand what's going on here a bit. So rather than just treating these like equations where we're subbing in numbers and getting to an answer, let's actually think what's going on here a little bit. And the first step I wanted to look back to was this heat balance term. So this heat balance term tells me what heat is coming in externally through my reactor surface area. What is the second term telling me? And there's a third term. Maybe we can interpret the third term first, or next. And this is all equal to 0. So this is saying this balances out. This first term is heat added or removed artificially. What does this last term represent? How much heat is being released from the reaction? So this is heat released due to reaction. Greater conversion multiplied by greater flow in of my species, that's going to release more heat. This is telling me how much heat I'm adding or removing. What is the sign of Q in this example that we just looked at? For this system. Is Q positive or is Q negative?
The negative, you can
I'm asking.
negative.
Okay. So Q is negative. So we've got T naught coming in at 450. We've now established that the temperature leaving over here is 373. My ambient temperature entering my jacket is at 300 and, what was it, 300? Q is the amount of heat being transferred from the jacket to the reactor. So is Q negative or is Q positive? Negative. So Q's sign is that it's the heat added to the system. So if I've got temperature here inlet at 450 Kelvin, my leaving temperature is 373, there's heat traveling from the reactor into the jacket. So heat is leaving the system. Well, what is the quantity of that heat in joules per second? How much is that? What is that Q dot value up there? Numerically. So we've looked at that equation before. What is Q dot for the system? $40,880. No.
43,000.
No. Negative. What's the formula for it? Okay, so let's take a look at that Q term. Q is equal to U times A, T ambient minus T. 560 multiplied by T ambient minus T, so 300 minus 373. Okay, so Q dot in this situation is minus 40,880 joules per second. That's the rate of heat leaving the system. Let's take a look at that last term, the heat of reaction term. And what I'll just do before we get to that point is to just do what's standard in the textbook, is we actually divide this equation out by FA naught. So we generally represent this divide by FA naught. Take that FA naught out, take that FA naught out. Okay, so let's report actually Q dot divided by FA naught here. So now let's divide by 1.3 moles per second. And we'll get a value that's equal to minus 31446. So that's joules per mole. So this is heat added or removed. This last term then is heat released by reaction. Anyone got an interpretation for this Cp times T term here? That's enthalpy coming in and out. And if it's positive, we've got more heat flowing into the system and leaving. If it's negative, we've got more heat leaving. Okay, so it's quite instructive to look at what these numbers are and where the relative amounts of heat are being transferred. So that first term there is minus 31,446. Let's look at that enthalpy term. So Q dot of FA naught. This enthalpy term is minus Cp naught T minus T naught. So we've already started with that's minus 31,446. This term over here, if you calculate it out, is plus 16170. So temperature 373 minus T naught of 300 multiplied by Cp naught, which we calculated earlier, of 210. And then our final term is heat release. That's minus. Sorry, yeah, minus 450. Thank you. Yeah, that's why this is positive. So 373, yeah, positive. And then this final term, minus the heat of reaction, minus the heat of reaction, gets me minus, times the minus gets me a plus 15386. So you notice those numbers don't quite balance out to zero. It's because I've got a little bit of inaccuracy there in estimating that temperature. But for the most part, this is telling me this is heat removed. This is enthalpy change. And this final one is heat generated. Anything you notice about this system that's kind of interesting? When you look at those numbers and balance. This material is coming in at 450 Kelvin and then leaving at 373. That's what this big enthalpy change term is representing. So when we're removing heat, we're removing 30,000 joules per mole of heat. We're only generating about half of that comes from the heat generated from the reaction. The other half comes from actually cooling down the material. So this isn't just a reactor, this is also a heat exchanger. Right? We're not just simply removing the heat that comes from the reaction, we're also cooling the material in addition to that, right? So I could actually get by, if I came in at a lower temperature over here, I could actually get away with removing less heat. So if I'm looking at optimizing this process's energy profile, it would be very straightforward for me to rather bring in, if possible, so we don't know what's coming upstream and we don't know the reason for this entry temperature being 450. But if we could cool that down in some way, I've got then less enthalpy coming in, and then I can get away with less, having to remove less heat out of the system. I can reduce the load on my utilities in this particular process. In fact, you can pretty much get away with any heat removed by just noticing that these two numbers balance pretty well. Right, so the amount of heat you're generating is being taken up as enthalpy there. So that's instructive. And what we do is, in fact, we call these terms over here, we call this R of T. So R of T is the heat removed from the system. So it's the heat coming in and out by Q as well as the enthalpy terms. And then we call this term over here plus G of T. That's the heat generated. And that's going to be set equal to 0. And so you'll see this notation in Vogler's textbook. So let's just write it out here that R of T is equal to Q naught over FA naught minus CP naught T minus T 0. And G of T is equal to the negative heat of reaction multiplied by conversion. So generated heat, and then we need to, this heat that gets generated, we have to ensure that all the heat that gets generated at a particular point of temperature. So if I choose to operate my reactor at higher or lower temperatures, this G function will change. So whatever heat gets generated by the system, I need to ensure I remove it in two ways, either externally through Q or through this enthalpy term over there. And really the only way I can adjust that is by adjusting T naught. What's going to happen to the system if the heating fails? If some operator comes by and shuts this valve over here to either the entry or the exit from the heating. There's a valve over here. When that valve gets shut, what's going to happen right away, the moment that valve gets shut, and what's going to happen long term?
So I'm assuming that because we're still have a shell of 450, because it's a shell temperature, so it's going to increase approaching 450.
The shells,
So yeah. So it's not getting cooled.
okay, so there's no flow here anymore. This valve is shut. So this, we're not seeing this inlet and outlet through here, this cooling material. What's going to happen to T, this reactor temperature level? This is T. It's going to increase for sure. Where is it going to increase to, or? It's going to be below T naught, above T naught, above T naught for sure. So we've got an exothermic reaction occurring. Now essentially what we have is an adiabatic system. Okay, so we can simply set Q naught over here to 0, and it becomes an adiabatic system. What's going to happen to kappa? What is kappa defined as for an adiabatic system? Kappa is going to be 0. Okay, so for no heat transfer, kappa is going to be 0. What is Tc? So if there's no heat transfer, if kappa is 0, if you go look back at the definition for Tc, Tc reduces down to T naught. And then what you can do is you can solve the system of equations that's out there and find what happens to conversion and what temperature you get. So let's just write that out quick. What you'll find then is that take that heat balance equation. So if Q dot is equal to 0, so in other words, you're doing a risk analysis essentially to understand what will happen in your process when an operator mistakenly closes this valve or it gets plugged in some way. So we'll do a lot of this in the 4N course. We'll do hazard and operability studies. What is the risk of some idiot operator having to close that valve? Is it going to cause a safety issue in the process? Or it might be an idiot engineer that's trying to do the plug or they can play around with the system. Is it going to cause dramatic failure? So we use our knowledge here. Q naught is equal to 0. We can quite easily find that Cp naught, T minus T naught. Now, this term goes away in my R of T. R of T must equal plus, sorry, R of T plus G of T must equal 0. So Cp naught, T minus T naught, that's equal then to the heat of reaction times the conversion. So we can quickly solve this and find out what's going to happen to that conversion. What you will find here is that we won't go through it because again it's a trial and error process. You'll find that temperature ramps up quite dramatically to 580 Kelvin. And I forgot to record the conversion when I was doing this. So I don't actually know what happens to the conversion here at the top, but it's quite easy to calculate it from this equation here. Okay, so it's guess and check. And you'll find that it ramps up to be a very hot system, 580 Kelvin, much warmer than that inlet. So that could be a safety hazard depending on the materials of construction and the environment around it. It may lead to very rapid boiling of this liquid, and then that's a safety issue as well. So again, don't just plug into these equations and treat them as equations. Actually think about what these individual terms mean and how they might change. The final, did you have a question? The final thing I just want to investigate here is what is the amount of coolant flow we need through this jacket. Right? So we had made a fair assumption a fairly important assumption last time that to derive that equation, we assumed that T ambient coming in, we call that T ambient 1. T ambient 1 coming in is equal to T ambient 2 leaving. But we know, as from our heat transfer courses, that if those two temperatures were identical to each other, that we're not actually really getting heat transfer. But we assume that at least T ambient 1 was somewhat or close to T ambient 2. Let's just go back then and look at that assumption a bit and investigate what happens with the numbers on that. And it will also help us estimate what our heat flow, our mass flow needs to be for this coolant. So we come back here to the equation that Q dot is M dot, the mass flow of our heat transfer medium, multiplied by the heat capacity of the heat transfer medium, times T ambient 1 minus T ambient 2. But we also have that is equal to U times A times T ambient minus T. And Marina calculated that earlier as minus 40,880 joules per second. Joules per second. So what we can do is we can now use this equation here and say, well, let's take a look at it. Let's assume T ambient is at 300 Kelvin. And let's assume we'll tolerate about a 2 Kelvin increase in our coolant water. So this then leads at 2 degrees higher. What is the mass flow I need to accommodate that? So let's use the heat capacity of water, since that's the most common heating material. So that's 4,180 joules per kilogram Kelvin. So 4,180 joules per kilogram Kelvin. We're going to take a temperature difference of 300 minus 302 Kelvin and solve then for this M dot. For our heat transfer medium in kilograms per second. So the units will cancel and get us kilograms per second. Notice here that there's a negative heat on this side because we're removing heat from the system, but this is also negative over here. Our ambient temperature leaving must be warmer. So it is consistent. We won't get a negative mass flow. That's good. So my heat transfer medium flow rate for a 2 Kelvin rise corresponds to 4.88 kilograms per second, or about 5 liters per second. That's a phenomenal flow rate. That's really high. If we only want a 2 Kelvin increase in my temperature leaving, I have to really pump water through there at quite a rate. So we can quickly trade off here. Well, let me accept a 5-degree rise. So for a 5 Kelvin rise in coolant temperature, we'll find that the mass flow of the heat transfer medium comes out to a more acceptable number in the order of 1.95 kilograms per second. Or about 2 liters per second. Okay, so even 2 liters per second is still on the high end to be flowing through tubes and pipes, but it's definitely a more reasonable value. Okay, so again here we did make this assumption earlier on, and it is a fair assumption to make, but it's not 100% accurate. However, we can come back and revisit this and understand what those numbers mean in terms of mass flows. So the point here from this class this evening is when we're looking at problems, not just to solve them and get to the final answer. We got our temperature, we got our conversion, but actually interpret these individual terms in these equations. Play around with it, see what happens if you set one equal to 0 under a fairly realistic case where someone closes the valve, for example, and Q0 goes away. Or what happens to conversion if T is equal to T0? Or what happens to my process when conversion is 0? Okay, so essentially, if I'm just flowing A into my reactor and nothing is taking place, there's no conversion, there's no heat released, does this equation make sense? Let's actually take a look at that, because this is one thing that trips people up all the time is they get their signs mixed up and they get negatives appearing when they should be positives. Well, one easy way to check that you've got your sign convention correct is, let's just take that first equation over there, this heat balance that we started this evening off with, and let's set conversion equal to 0. So assuming I'm just feeding in my reactants, and for example, I've maybe not added my catalyst, or I'm not starting my reaction in some way, so I'm getting no conversion. So what occurs then is that Q over FA naught, well, let's sub in that. Q is UA times T ambient minus T divided by FA naught. If this whole term over here on the right hand, on this heat of reaction times FA naught times X is equal to 0, I can take this term over to the other side. That's equal to Cp naught T minus T naught. So let's take a look at that. If T ambient, my cooling temperature or my heat transfer medium comes in at a temperature greater than the tank temperature, that implies that T is greater than T naught. And that makes absolute sense, because now my temperature gradient is that I'm taking heat from my jacket and putting it into the tank. So that must imply, we expect that my temperature leaving must be greater than the entry temperature. That's a great way to make sure that you don't have your signs flipped around. Sometimes people write this equation as UA times T minus T ambient.
Okay, that's a very good check now. We can quickly make sure that my signs do make sense and match up with what I expect. In fact, people will, I guarantee that there will be a number of you in the exam that will like this as T minus T ambient, because it appears like this in Fogler's textbook at certain parts, and then midway he switches his signs around. Okay. So if you've gone and picked the wrong equation, you will get this conversion, or this convention incorrect. Again, let's flip this around. If my coolant is now actually a coolant, so it's lower than the tank temperature, that implies my temperature leaving must be lower than my inlet temperature. Again, that makes sense. If we've got no reaction occurring, no heat being released or generated by reaction, if my temperature of my jacket is lower than the tank temperature, it implies my temperature leaving must be lower than the inlet temperature. So always explore your equations like this and make sure they match up with what your expectations are from an engineering perspective.